Hello and welcome to the OLLI NOAA Climate Change Short Course. I'm David Herring, Director of Communications and Education within NOAA's Climate Program Office. And on behalf of NOAA and our partners in the Osher Lifelong Learning Institute, it's a pleasure to bring you this lineup of world-class climate science experts to give an overview on our modern understanding of Earth's climate system. Today we're going to hear from Dr. Anthony Janetos, who is going to present a detailed look at global climate change impacts in the United States. Today's presentation is going to make it clear that the effects of climate change aren't some faraway thing far off in the future, but are actually being felt right here in the United States, in people's lives, in the economy, and in our natural resources. So please join me in welcoming Dr. Anthony Janetos in this presentation on climate change impacts in the United States.
I do want to say a little bit about my background. I'm actually trained as an ecologist, and for about the past 25 years, I've worked on a variety of programs that are all related to the way that terrestrial ecosystems interact with the atmosphere, whether it's a question of responses to pollution stresses or acid rain. But the most challenging of those problems is understanding the detailed relationships between ecological systems, natural resources, and the variability and change in the physical climate system. And so that's really what I want to talk to you about today. And I'm going to focus on several things. I'm going to want to talk about the impacts of change and variability on a whole variety of natural resources, but also on some other sectors about which we care, on coastal systems, on human health, and so forth, transportation, and so forth. I'm going to draw primarily on the results from several national scientific assessments that have been done over the past decade. I'll show you each one of those. I'm going to spend some time on projections of change, but mostly what I'm going to talk about are current observations and our conclusions from things that are going on right now in these systems. At the end, I want to say a few things about both adapting, that is coping with changes and stresses in natural resources, and I want to highlight what I think some of the continuing challenges for the research enterprise are. And as Alan said, my major focus in this talk today is going to be on the U.S. I learned long ago that you tell people what you're going to say, then you say it, and then you tell them what you said. So what I'm going to say is that we are in fact seeing a whole variety of climate-driven impacts in a wide variety of sectors in the U.S. and indeed internationally on ecosystems and natural resources, on water resources, on agriculture. That's not by any means a comprehensive set. I just put these up here for illustration. Secondly, that risks are likely to increase over time, and there's a variety of reasons for that. And third, that attribution to anthropogenic climate change, to human-driven climate change, is difficult because impacts are always multiple stress problems. They're not simply a result of what happens to the climate system. They're the net result of lots of different stresses and pressures. Well, let me start with a couple of fairly basic observations about the physical climate system and about the composition of the atmosphere. And I know the previous speakers have probably addressed some of these things, so if you'll pardon me maybe for retreading some old ground, what I want to start with first is atmospheric composition. We know, in fact, quite a lot about the concentration of greenhouse gases in the current atmosphere. In fact, these are actually old data. This graph was, these data are probably about 10 years old, but these are actual measurements. These are recent measurements, recent meaning from about 1950 to the present, are direct atmospheric measurements, first from Mauna Loa, then from a whole network of monitoring stations around the world. Previous measurements are basically measurements of CO2 concentration from ice bubbles that have been captured in air bubbles that have been captured in ice and are actually pulled out of ice cores. This record actually goes back now about 400,000 years because of analysis from some very long forests from Antarctica. But I want to focus only on the past 1,200 years or so. And what we see here is really pretty clear. As is typical of most interglacial periods, and has been typical in today's world for about the past 10,000 years or so, for many, many years, the concentration of CO2 in the atmosphere is remarkably stable. It's around 280 to 285, maybe up to 290 parts per million by volume, until the Industrial Revolution. And what's happened since the Industrial Revolution is also really very clear. We've seen a continuing rise of CO2 concentrations. We are currently up to about 390, 392, 393 parts per million. And there is essentially no scientific uncertainty about why this has occurred. About half this increase, some 45, maybe 50%, is actually the result of clearing of forests for expansion of agriculture. The other half is from combusting fossil fuels. And the reason that we know that, and there hasn't been any real uncertainty about this for about the last 50 years, the reason that we know that is because of the isotopic composition of the carbon in the atmosphere. The carbon that gets captured by plants is still what we call live carbon. The ratio of carbon-14, the radioactive isotope, to carbon-13 or carbon-12, mostly carbon-12, is well known. We know what that looks like in living tissue. But when you burn fossil fuels, what you're doing is burning carbon that is hundreds of millions of years old. And essentially all the C14 has decayed down to C12. And so that changes the isotopic ratio of carbon in the atmosphere in a way that is really very clear. You know, you can calculate it. And what has clearly happened when you look at the isotopic ratio of the current concentration of CO2 in the atmosphere, it is pretty much exactly what you'd expect as a mixture of this burning of what we call dead carbon with the live carbon that is exchanged every year between the atmosphere, the biosphere, and the ocean. So it's really quite clear that over the last 150 years or so, we've seen this increase, which is now around a 35% increase over the natural baseline, is the result of these two features. Clearing of forests, mostly for agricultural expansion, and burning of fossil fuels. Over the last 60 years, basically since the end of the Second World War, the vast majority of the extra carbon is from burning fossil fuels. And in fact, in today's world, over the last several decades, the clearing of forests for agriculture is mostly a phenomenon of the tropics and subtropics. It accounts for somewhere between 15 and 20% of the annual contributions of fossil fuel, or the annual contributions of CO2 to the atmosphere. The rest is fossil fuel combustion. So we are now in a world where about 80% of the annual contribution of extra CO2 to the atmosphere is directly from the combustion of fossil fuels. Whoops. We've seen a variety of changes in the physical climate system. I won't go through too much on the global side. As you would expect, these changes are not uniform over the world. If you look only at the U.S., for example, these are actually data from NOAA and the U.S. Geological Survey. There are big parts of the U.S. that over the last century or so, basically during the 20th century, have seen either modest to, in some cases, in Alaska, for example, really quite large warming trends. There are places in the U.S. where this is not true. Southeast, for example, has largely, during this time period, had largely seen a cooling trend. Precipitation is much more variable, as you would expect, and there's some indication that there's decreased precipitation in the southwest and in parts of the mountain west. In the east, this is not so clear. These aren't big changes. I'm going to show you a little bit more about this in the talk to come. And then if you think about the future, and I know you've had a presentation on the physical climate system and climate models. While the models differ in their quantitative details, in general terms, they're really quite similar to each other. And depending on the particular emissions that you assume will happen, they all show this feature of enhanced warming over the 21st century and or into the 21st century and through the 21st century, and big changes in precipitation, which typically have the pattern of more precipitation as you go towards the pole, but areas in particular in North America, in the west and southwest, that appear that they're going to dry out quite substantially. So internationally, the way that the conclusions that people have drawn about both the patterns in the climate system and changes in the impact of those changes were summarized in the last IPCC assessment this way. The observed change in the climate system is virtually certain to be due in part to human influence, that these changes are very likely to continue and even accelerate during the current century, particularly if emissions of greenhouse gases remain on their current paths. And there are now many, by which we mean thousands, of observed, very well documented impacts of changes in natural resources, in animal and plant species, their distributions, their phenological patterns, and ecosystems in many, many regions of the world, and that these impacts are very likely to grow in both number and magnitude. And that those impacts already present challenges for adaptation in the developing world, as well as among some of the developed countries. And so, having said that, I just want to show you a couple of pictorial examples of this sort of thing. So these are, this is a couple of photographs of glaciers. This is Grinnell Glacier in Glacier National Park, photograph taken from the same spot. So about 60, well, not quite 60 years apart, about not quite 50 years apart. This is what this glacier looked like in 1938. This is what it looked like in the early 80s, largely retreated with this pool of open water down here. In Muir Glacier in Alaska, over a period of about 60 years, shows a very similar phenomenon. And in fact, this is a very common phenomenon in most of the landlocked glaciers around the world, where they've been retreating, they've been melting, they've been retreating much faster than we had previously seen, and with only a few exceptions, this is a worldwide phenomenon. So, how do we think about this, and how do we think about this across different sectors, and for impacts on parts of the U.S. that we care about? In fact, there's a mandate for the research programs of the government to do periodic scientific assessments. This mandate was actually in the 1990 law that established the U.S. Global Change Research Program, and there have now been a series of scientific assessments of these impacts, the first of which was this one. This one was published in 1990. I was fortunate to be one of the co-chairs of this. And what we did in this assessment was begin to examine the evidence and look at some of the impact models that we had. And we have a whole, I'll just summarize a few things. I won't take you through this entire table. But for different types of ecological systems, for forests, grasslands, tundra, arid systems, coastal systems, we looked at the evidence for a variety of different kinds of impacts, whether it was changes in tree species composition or an alteration of habitat, or whether it was loss of alpine meadows through climatic effects. And then we tried to identify for different parts of the country where those impacts either were occurring or were likely to occur as the climate system continued to change. And so some of these impacts, for example, changes in tree species composition, we thought could end up being quite widespread across the country. Others are really much more particular. There aren't, after all, a lot of alpine meadows around the country. They're concentrated in particular regions. This increase in woody species and loss of desert species was really a particular conclusion for parts of the West. And what we tried to do was assess the scientific literature and a series of modeling studies as to how likely we thought these were to occur, and then summarize this in about a 100-page report with visuals that we hoped would be instructive. And so this is another way to depict these kinds of results where, for example, in Alaska, we've already seen substantial melting of permafrost, changes in fire frequencies, and so on. And we laid out the scientific foundation for each one of these conclusions. The second one of these scientific assessments was this one, and this is a much more detailed report. This is sorry, I'm getting used to this clicker. This title is Effects of Climate Change on Agriculture, Land Resources, etc. And this is what the research program called Synthesis and Assessment Products. So this is really an exhaustive review of the literature as it stood about 5 years ago on impacts of changes in the climate system on a whole wide range of resources. And so let me just take you through a couple of the overarching conclusions before I go to the third assessment. And in this one, so this is now about 5 years ago, we concluded that climate changes, both temperature increases, increasing CO2 concentrations in the atmosphere, and altered patterns of precipitation are already affecting water resources, agriculture, land resources, etc., that it will continue to have significant effects on these resources over the next few decades and beyond. But of course, that many other stresses and disturbances are also affecting these resources. Secondly, that impacts on these ecological systems are very likely to impact the services that they provide for us. And so this was really kind of a new concept as compared to the first report, recognizing, as has become clear in the scientific literature, that there are many things upon which we depend that come from ecological systems, whether it's sequestering carbon, regulating water flow, maintaining soil fertility, a whole host of providing habitat for wild species that we really do depend on, but for which we do not pay. They're not priced in markets. They're not traded in markets. There are many other things that we depend on, supply of timber, food supply, for which that are traded in markets that have known prices, that we managed ecosystems in order to obtain them. And what we concluded in this assessment was that in particular, those services that ecosystems provide, but for which we don't actually invest, that don't have a tangible economic price associated with them, are in fact vulnerable. But it's very difficult, given our current understanding, to project the consequences of changes in the services as opposed to simply changes in the resources. Secondly, we were asked specifically to comment on the ability of the government to monitor climate change impacts, something we had not been asked to do previously. And our conclusion here was that there are many different monitoring systems, and they're useful for a whole wide range of purposes. There's substantially less overlap amongst them than you might think, but they're not optimized for detecting the impacts of climate change on ecosystems. They're all optimized for something else. And so a lot of our knowledge is, in a sense, serendipitous. We've been able to adapt these monitoring systems or research areas for other purposes to try to figure out
what the change in magnitude or rate of change in impacts actually is. The third of these assessments was then published just a couple of years ago. This one goes beyond natural resources, although I'm going to return to the natural resources part as well, and begins to look at other sectors as well. Health impacts, transportation impacts, energy impacts, and so on. And so I'm going to spend considerably more time on this and weave in some of the conclusions from the previous assessments as well. Here again, we took both the sort of national approach, but also looked at the regional texture of impacts in different parts of the country. We looked primarily in this assessment at 7 different sectors: at water, at energy, water, agriculture, transportation, natural ecosystems, health, and broader societal effects. And so let me run through some of these key findings. And the first I'm going to talk about are water resources. And one of the really key findings here is that climate change will stress water resources, and there are parts of the country where this is already happening. And so if you look at it in a sense from the supply side, we've already seen a change in the statistics of rainfall. We've seen in the observational data up to, this is probably around the last year for which good data are available, observed increases in the percentage of rainfall that occurs as heavy downpours. And so the percentage in each one of these different parts of the country is the percentage change in heavy downpours. And you can see in some parts of the country, the percentage change has really been quite dramatic, that the northeastern states have seen the incidences of heavy downpours increase by about 2/3. A really quite dramatic change. We took also a look at under a couple of at some climate model results for the future to try to understand, is this trend likely to continue, or is it just a statistical anomaly of the past 50 years or so? And it appears in the model output that whether it's for a high emission scenario or a slightly lower emission scenario, that you would see similar consequences for the future, that the heaviest downpours, no matter which emissions trajectory you are on, would also continue to increase over the 21st century. At the same time, in the observational data, we took a look at what was happening to drought. So drought is not just a function of rainfall, after all, it's also a function of water demand and soil moisture. And so what's happened in the U.S. from the late 50s to the early part of the 21st century in terms of drought trends is really quite striking. Most of the U.S. has actually had a trend of decreasing drought. There are parts, however, that have had trends of increasing drought, in particular through the West and Mountain West. Some indication recently in the Southeast, over a century this is not so clear, but recent variability in the Southeast is certainly indicates that some drying out of that part of the country. If you look at again at the precipitation that occurs in the winter, observational data already show that there's a change in the contribution of snowfall to wintertime precipitation, with the red dots meaning less snow, and the blue squares here, areas where there's actually been more snow. And the pattern across much of the country, in particular the Midwest and Plains states, and especially through the Northwest, is less of the wintertime precipitation. A smaller fraction of the wintertime precipitation arrives as snow. These are also trends from around 1950, the middle part of the 20th century to the early part of the 21st century. And we combine these and have been able now to start looking at projected changes in runoff. So we're getting closer to how much water is actually available to be used. Not just how much falls, but how much actually runs off and is therefore available as surface water to be used. And so if you, there are several studies in the literature that have done this kind of analysis, and again, they tend to have this sort of consensus result. They're all quite similar in their results, that in particular, the West, in particular the Southwest, and parts of the Mountain West are likely to show some quite dramatic declines in runoff, while other parts of the country, changes appear rather either more moderate or even small increases in runoff. So what do we conclude from this? In most of the U.S. has actually seen either increases in precip and stream flow, decreases in drought. These trends are actually understood now to be a combination of long-term change, in part anthropogenic change, and decadal scale variability, a function of some of the natural oscillations on scales from decade to decade in the climate system. There's some indication of increased drought severity and duration in the western and southwestern U.S., and in fact, parts of the West have seen historically very large droughts for about the past 30 years. But we are now observing a trend of reduced mountain snowpack and earlier spring snowmelt runoff across much of the western United States. And there are now several studies in the literature that attribute this really quite directly, in part to long-term warming due to anthropogenic changes, due to human activities. There's some fraction of this that is also probably mediated by natural variability, but the long-term trend is really fairly clear. This trend is particularly in snowmelt peaks and therefore reduced summer flow and fall flows have already been detected. So we've already seen the impacts of this change in the precipitation regime on actual water management in the West and in the Mountain West. And everything we know about the underlying science suggests that these shifts are likely to continue. And they're already having an effect on how some large reservoir systems in the West are managed. Because what is happening is less of that, essentially, for the Mountain West, much of the water storage is in the snowpack. And so the challenge is, how do you manage that flow when the snow melts? And when the snow melts early, as has been happening and is projected to continue to happen in a warming climate, you get that water too early, and if you don't have a reservoir system that's adequate to store it, then you have a water management challenge. You get the water early when you don't really need it. When you really want to have it in the middle of the growing season, there's less of it left. And so this is already providing pressure for reallocation of water, and managers in many water systems in the West are already having to rethink how they actually manage water supplies. This turns out to be a major focus of state-level scientific assessments and impact assessments that the state of California is doing, for example. Let me turn my attention a little bit to forests, and this is an area where that has received a lot of attention. In this case, you may not be able to see this very much. In this case, we use some research and modeling from the U.S. Forest Service where they've done a tremendous amount of research on different species of trees in the eastern deciduous forests of the U.S. This is one of those. These happen to be results for sugar maple, and this is the current situation. This is the distribution, a map of the current distribution of sugar maple, and this is what's called an importance value, which is simply an index of how prevalent sugar maple is in different parts of the country in the Northeast. And this is sort of the lower boundary or the most southerly boundary of the range of sugar maple. And this pretty much represents where sugar maples are today. What we then did was say, okay, under a doubled CO2 atmosphere, under an atmosphere that's sort of doubled from pre-industrial conditions, for about 550, 560 parts per million, a level that under current trends we will reach somewhere between the middle and the second half of the 21st century, what happens to the climate conditions that are optimal for sugar maple? And therefore, what is likely to happen at equilibrium once to the distribution of sugar maple when it comes into equilibrium with the climate? And what mostly happens, depending on the details depend a little bit on which climate model you use. So we looked in this study looked at 5 of them. What mostly happens is that the optimal climate conditions for sugar maple leave the U.S. And in fact, that this change in the climate system that's projected is large enough to make it, in fact, quite unlikely that one of the most common species of trees in the eastern deciduous forest could successfully reproduce itself and continue as an element in the eastern forest. Now, I have to tell you a little story. We did the first installment of this research, even in the very first national assessment, so now more than 10 years ago. And I grew up in New Hampshire. I grew up on the New Hampshire seacoast. So I thought I knew something about how important people thought sugar maple was. And so even in the first assessment, we had the first slightly less detailed results of this. We thought, all of us ecologists, we thought we were being so clever. We published all these results on what would happen to the carbon balance of the forest, and that the ability of the forest to sequester carbon from the atmosphere would decline. And we thought, well, everybody's going to be really excited about this. But no, everybody was really excited about sugar maple. And I think the reason was that this is really kind of an iconic species particularly for New England. This is what gives the fall foliage its sharp colors. This is why people, fly to Boston and drive up the interstate up into the White Mountains and the Green Mountains in the fall, and why all the local weather stations have a fall foliage map and fall foliage predictions all through the fall. It's culturally important. Sugar from sugar maple is a little niche industry. It's a little mom and pop shops, and maple syrup is not a big part of the regional economy. Tourism is, but most importantly is that I think this is one of these kinds of impacts that affects people's sense of place. That this is not the way we grew up. This is not the same kind of place where we grew up. If we come back to the science, for forest resources, it's already quite clear that climate change has very likely increased the size and number of forest fires. This is especially prevalent in the West, but it's also changed insect outbreaks, and I'm going to come back to this. And we've seen some large episodes of tree mortality in the interior West, the Southwest, and Alaska, and we'll continue to do so. And this is also another one of the climate-related impacts that in the scientific literature has already been fairly directly attributed to anthropogenic change. The big issue about forests and vegetation, and we'll come back to it for agriculture, is that CO2 by itself is required. And in fact, plants respond strongly if they have enough water and nutrients to increasing CO2. They photosynthesize more, they draw more carbon down from the atmosphere. But we now have 10 years of experimental data on actually artificially adding CO2 to the atmosphere of forest stands, or to grasslands, or to mixed stands. And what we thought was going to be really a quite large effect turns out to be both smaller and simply different than we had imagined. And in fact, when you experimentally add CO2 to forest stands, what tends to happen is they will photosynthesize faster and store more carbon for a while. They tend to put that carbon in fine roots in the soil and in twigs. They don't tend to put it into increased wood production in the boles of the trees, in the trunks of the trees. We actually don't understand why that particular physiological allocation of carbon occurs, but that is what they do. And so while it's likely, very likely, that this rising CO2 is going to increase photosynthesis for many forests, it's probably going to occur, given our current understanding, it'll probably only increase wood production on very young forests that are still growing rapidly, that are already on fertile soils. That this is one of those effects that requires other resources, availability of water, availability of nitrogen in the soils, and so forth, to actually be expressed in the natural world. At the same time, we've had decades of increased deposition from the atmosphere of nitrogen, partly from fossil fuel, well, mostly from fossil fuel combustion, partly from the energy sector, but more than half of it from cars and from automobiles and trucks. And we have had increasing temperatures, and they have also likely increased forest growth where there's been enough water, and are likely to continue to do so in the near future. And if you look at forest soils, we really know relatively little about what's going on in forest soils. And so how the soils that support forested ecosystems will respond is still a big scientific challenge. We then turn to crops. Crops are interesting because we manage them, obviously. We care a lot about them. We manage them quite directly each year. There's a lot of experimental work on the CO2 response of crops, and the results for the CO2 response of crops are in general terms, the crops, like most other plants, prosper. They grow faster when there's more CO2 in the atmosphere, as long as there's enough water, as long as there's enough nutrients. But of course, the beauty of agricultural systems is that we make sure there's enough water and we make sure there are enough nutrients. But what's generally not so much appreciated about crops is that they have their own temperature sensitivities. And so these are the optimum ranges, optimum response curves for corn and soybean, that contrast two things. And in the green curves is the optimum range for growth, just for getting the plant out of the ground. How high is it going to grow? How much carbon is it going to sequester? And the purple curve is the optimum temperature response for reproduction, for pollination and seed set. And so there are a couple of things that one wants to notice about this. And one is that these are not nice symmetrical bell-shaped curves. Like lots of physiological functions, like lots of our physiological functions, they tend to rise slowly, and at the high end, they drop rapidly. So the upper threshold is actually quite close to the optimum. So there's not much space, physiological space, for increases in temperature. Secondly, for crops, well, you do care about how much it grows, but what you really care about is the reproductive phase, because we eat the seeds. And so the optimal temperatures for reproduction tend to be lower, and sometimes much lower, than they are for growth. And in fact, corn will fail to reproduce at temperatures above about 95 Fahrenheit, and soybean at temperatures above about 102. So there's nothing mysterious about this. This is well known in the agricultural literature and to agronomists, and different varieties have slightly different curves, but this is a really fairly common phenomenon. So it's actually important for agriculture to think about both the CO2 increases and changes in temperature. And so the joint effects are what we've started to look at. And what typically happens for the big cereal crops is that the life cycle of both the grain crops and oilseed crops is likely to progress more rapidly. This sounds on the face of it like it should be a good thing, and sometimes it could be, but what happens particularly for the grains is that means there's actually less time available for the plant to fill the seed with carbohydrate. So you might get a corn or soybean that goes through its life cycle more quickly, but the seeds are smaller. And they have less carbohydrate available. The nutritional quality is less than it would otherwise be. And as the temperature rises, and in particularly if there are changes in variability, we could see the experience of crop failure increase, and so this is where a lot of research in the agricultural sector now is trying to focus, is trying to understand these joint effects of CO2 and changes in the physical climate itself. It also turns out that what people typically look at are the big commodity crops. We care about wheat, we care about corn, we care about soy, but the horticultural crops, tomatoes, onions, fruits, basically fruits and vegetables, have had much less attention, but they also turn out to be much more sensitive to climate change than the big grains and the oilseed crops. It's also important to remember that crops are not the only thing in the fields. We've already seen in the U.S. Midwest the beginnings of a northern migration of a lot of weed species for reasons of the differences in the ways, the biochemical pathways, the way they photosynthesize. Many weeds actually respond more positively to increasing CO2 than the crops that they're competing with. And this is particularly true for some of these quite invasive weeds. And in addition, we're already starting to see an increase in pest and disease pressure, both for crops, but also for animals, for animal husbandry. We move to coastal features. So coastal areas, we've already seen an increase in sort of dollar amounts of damage. That's a little misleading because, after all, we've seen tremendous coastal development over the past 50 years. And so a lot of the increases in dollar amounts of the damages from big storms and things like that are a joint effect of changes in sea level and simply changes in patterns of development. But if you look only at sea level, so this is a depiction of data largely from the U.S. Geological Survey. If you look primarily at sea level, the arrows that are pointing up are places where the local sea level is rising. The degree of redness and the size of the arrow indicates where this change is large, or conversely where it's small. There are parts of the U.S. Where local sea level is actually falling, where the land is still rebounding essentially from the loss of glaciers at the end of the last glaciation, and that's particularly prevalent in parts of the Pacific Northwest, some parts of northern New England up here, but in much of the U.S. and especially from the middle of the Atlantic seaboard, sort of down the Atlantic seaboard, and of course in the Gulf, and even down into Florida, the local sea level, so the combination of a rise in the open ocean sea level and what's actually happening to the land that it abuts, is a very large effect. And so even locally here on the Chesapeake Bay, we're seeing very large local rates of sea level rise in the Newport News, Hampton Roads area in Virginia, where all the naval installations are. We're seeing very large changes, very large rises of local sea level. And of course in the Gulf, where we have this combination of a rise in the sea level and this very rapid subsidence of the shoreline for a whole variety of reasons, most of them in the Gulf at least human-caused. And we can begin to take a look at how that risk might change. And so we'll look at the most conservative estimates, which are the IPCC estimates about sea level rise. We've converted the units from meters to feet, since we were writing in this case mostly for a U.S. audience and mostly a congressional audience. And so, depending again on where you are, where you might end up in terms of greenhouse gas emissions, even the most conservative estimates for the end of the century are something on order of a foot to 2 feet of additional sea level rise. This only takes into account the thermal expansion of the ocean. Water heats up just like any other substance. It heats up, it expands. This does not take into account, or these estimates do not take into account the actual melting of the land-based ice sheets. So, what would a world that had, say, we've looked at a whole wide range of scenarios. What would a world that had a substantial amount of sea level rise by the end of the century look like? This is one illustration of what it might look like. These are the parts of southern Florida that are less than 3 feet above current sea level. So if you did end up on the high end of that range, well, Florida would look substantially different, I guess would be one way to say it. We were able, on the other hand, to take a very close look at the Gulf, and the Department of Interior and the Department of Transportation did a very detailed study of the vulnerability of the transportation sector in the Gulf. And this study, I was actually on the advisory board for this study. This study spanned Katrina. So this study began before Katrina hit, and then it continued after Katrina hit. And so we have, unfortunately, a very good natural experiment in vulnerability. What's colored in here on this these obviously are the road networks, the interstate highways, state highways, local roads. What's colored in this sort of bluish color are all the areas that are below 4 feet in elevation. They're below 4 feet above sea level. All of these areas were flooded during Katrina. And the reason the transportation people are interested in this is twofold. And one is that this is a part of the country that, until Katrina hit, was seeing substantial increase in population and development. And so they actually need to think hard about this in terms of future planning for where the infrastructure is actually going to be. The second reason is that the Port of New Orleans is the major port of entry for the vast majority of natural gas importation and oil importation in this country. And something like, I've forgotten the exact number, something like a half or 2/3 of all the natural gas that's imported to the U.S. comes through the Port of New Orleans. And in fact, Katrina instituted this hiatus in actually being able to use the port, and we did see a spike in energy prices as a result. Let me turn a little closer to home, and this is the risks to human health. So one of these risks is, of course, this is both a quality of life issue but also an actual health risk, is what happens to heat waves. All right? We've all been through a heat wave, and one of the features of heat waves is if they occur to populations that are unprepared for them, we actually have the possibility, and we have seen over time, substantial mortality result. We've been fortunate in the U.S. that we haven't had an event anything quite like what the Europeans have seen, where tens of thousands of people died. But we have had events where hundreds or even thousands of people have died. So if you look at the recent past, and so this is from 1960 to about 1980, the number of days that are over 100 degrees Fahrenheit, which is as one index of what you might call a heat wave, looks about like this. So these are, so here's the scale. Most of the country has very few days that are above 100 degrees. There are parts of the country where you get quite a number of days that are above 100 degrees. We all know where they are. And then what we did was look at two different potential climate futures, a low scenario future and then a high scenario future. And even in the low emissions future, the parts of the country that would see substantial increases in the number of days above 100 degrees broadens quite widely up through the Midwest and through the Plain States, and broadens widely across the West. If we were unlucky and ended up in a high emissions future, then by the end of the 21st century, the number of days above 100 degrees looks very different indeed than today's world. And this actually is enough that what we don't know is our capability to adapt to this world. In addition, we have known relationships between temperatures, ambient temperatures, and ozone concentrations. These are data from both Atlanta and New York. And so there have been a number of studies now that suggest that as the temperature changes and generally increases, that even if we had the same emissions of ozone precursors as today, we would simply see more ozone formed in the atmosphere. For the first time, we also then took a look at the energy sector, because it turns out that while agriculture is actually the biggest user of water in the U.S., far bigger than anything else, the energy sector is second. We use energy to cool coal-fired power plants. We use water to cool, nuclear power plants. You almost always are building new facilities near a sustainable supply of water for obvious reasons. And so this is an interaction that we really hadn't looked at before. And in a fairly comprehensive review of the existing literature, we concluded that there was a high likelihood that water shortages would actually begin to limit power plant electricity production. That we're obviously going to need more energy. The U.S. population continues to grow. And that even if all we saw were thermal effects, simply the warming up of surface waters, this reduces the efficiency of the current cooling technologies. You're simply not able to carry as much heat away. And we've got 40 years of research on the impacts of warm water discharges from power plants. Particularly for cold water fish species, we know a lot about how they respond or how vulnerable they are to warm water discharges. And so this is an area where we've only begun to scratch the surface of what this interaction between change in the climate system and a change in the energy sector would actually begin to look like. One of the last things I want to talk about are bark beetles. I'm going to come back to this a little bit at the end too, but we're already seeing changes in pest infestations in both agricultural crops, but especially in forests. So this is an example from Alaska. And we know that this phenomenon is triggered by a change in the climate system, in particular a change in winter temperatures. And I'll explain a little bit more in a minute about why that is. What we don't know is whether this trend is linked specifically to anthropogenic climate change. So as in previous assessments, we tried to summarize this for different parts of the country. And so we have a series of